Hello, everyone. Hope you are not too sleepy for this straight after lunch talk. But yeah, here I am. I'm presenting on behalf of my colleague, Gray, who couldn't make it because he's recovering from an infection. So I will be introducing some of the scope behind why we designed RMF and some of the features that it currently offers. Oh la la. All right. So first of all, what's the motivation behind the design of RMF? So we all think that robots are intelligent, especially people who are not in the robotics field, have this idea of the machines that will take over the world one day. It's really not the case. So what you see on the right is actually a scenario that took place in real life when we were working in the early development of RMF. So what happens is that if you try to bring in two different fleets of vendors into fleets of robotic, vendor fleets in your site, and then you try to have them to share space, what happens is that since they cannot communicate with each other, there is a high chance of deadlocking happening. So this is part on a true story. When we were working with the hospital, we would have one of the robots that would just end up in the corridor facing another robot from a different vendor, and this recorded voice from a speaker repeating, "Please move away, please move away, please move away," and the robot actually not doing anything. And then until they finally try to move forward, touch the other robot, and then it went into a safety stop, and then the whole thing just completely blocked the corridor. So the concept is that robots must be able to communicate with each other in order to be able to play a larger role in our lives. So to solve this problem, we developed OpenRMF. So we tackle different parts of this problem. So at the very least, the problem of how do we coordinate robots so they share space. So for example, if they all need to share a corridor or go through a junction together. And then on top of that, once they can share space, how do they share infrastructure? So if, for example, automated doors or automated lifts. And then once this is solved, how to make actually useful applications, which is how to make them synchronize with other devices, like for example, robotic arms or dispensers if you want to use your robots for deliveries. And then another constraint, a major constraint that we put on a system, that for now we are looking at moderate scale, so not super high density, super optimized sites. And these are some examples of places where we have successfully deployed OpenRMF, from hospitals, hotels, and libraries. So we are not dealing, for example, in the case of a dense warehouse that you sometimes see in these videos of these this super integrated, super efficient, high density fleets. So we're not dealing with that for the scope of these projects. So we have a few assumptions. So first of all, the main assumption of OpenRMF is that it is necessary for a vendor to have for a site manager to have robots from multiple vendors. And the idea is that there is not a single robot that can do everything. I think this was also brought up before. For example, when Maria was presenting some of the projects they've been doing at ROS-I, where, for example, if you in some site you need a cleaning robot that is able to do some cleaning, and maybe a delivery robot to deliver some items, as the people in Hop Technique were showing in their booths. So there is we assume that people need robots from multiple vendors. And then we also assume that different robots have different capabilities and offer different levels of integration. So each robot will have its own API, and each vendor will only give you a certain level of control, and we need to be able to deal with this problem. Also, we assume that real-life environments are dynamic and there is some level of unpredictability. For example, this is always the case. We have seen in hospital where there can be a lot of clutter, trolleys, nurses going around bringing patients, as well as the most obvious obstacle to a robot, which is humans. So people going around and blocking the robot's way and so on. So we designed the system to be able to react to these events. And then also the final assumption is that a centralized command of the fleet is not always an option. So of course we support it. So we support a system where we can take control of all the robots and control all of them. But what happens in real life is that if you bring a robot vendor, let's say robot vendor A comes in and says, "Oh, you need to use my proprietary solution to manage my robots. You cannot do anything else, and you need to deal with it." So we designed the system to be able to deal with different fleet managers. So what are the main focus, like design points of OpenRMF? So first of all, we, like all robots, operate on this concept of like a shared traffic schedule. So robots need to communicate to like a schedule management node what their intended trajectory through space-time is, where space-time is a very futuristic word, which literally just means the robot needs to say, I will be at this point, at this timestamp, and at this point, at this timestamp, and so on. And then we implemented like a negotiation to resolve conflicts. So as I mentioned just now, we don't have a centralized system, but we have a peer-to-peer conflict. So as soon as a robot from fleet A detects a conflict with robot from fleet B, the two fleets will negotiate with each other and try to solve the conflict. Then we also implemented a task system, an auctioning system for tasks, which basically for whenever a user tells the system, oh, I need to execute this task, like for example, like clean this section of the airport. Then the task will be dispatched to all fleets that can do it, and then there will be a bidding process to choose which robot will do the task. And we use a logic of lowest cost that I will cover a bit more in detail later. And finally, arguably the most important part is that we provide a stable SDA and API. So we want to keep improving the algorithms, and we want to keep improving our software, but we also want to make sure that people who decided to adopt RMF maybe 3 years ago, 4 years ago, when it was very early in its development, don't get penalized for adopting it too early when it was not as mature as it is today. So we maintain stable API in both C++ and Python, and we implement additional feature by improving and adding new functions to these APIs. And something that is not part of RMF, at least for now, is there is no concept of like a stable wire protocol. So the data that actually goes on the wire can change, but the idea is that since users only integrate with like the API or the SDK, the communication traffic is actually abstracted away from them, so they don't need to worry about it. So here we split like the main like OpenRMF in like 3 big blocks. So we have like fundamental components on the left that are just utility components that are pretty much like drop-in executables that you just like compile and run in your site, and you don't need to really worry about them. So some of them are, for example, like the task auctioning system or like the traffic schedule system. And then on the top right, we have reusable software libraries that like system integrators will deal with from time to time. So for example, to site one, we have like the web tools. So it's a full front-end and back-end system where people can like have a web dashboard where they see what the robots are doing, how they live, where the lifts are, where the doors are, and they can submit tasks, cancel tasks, and like everything they might need in a site. Together with a full like backend like database implementation that integrates with the rest of the stack. And in the bottom right, we have probably the part that each system integrator will deal with the most, which is the platform adapters. So all that you need to do to bring some, let's say, some new vendor, some new robot vendor, or some new door vendor into your system is that you need to have some sort of adapter that converts whatever proprietary protocol they have to what RMF is using. And this is the part that most system integrators will probably deal with the most in our experience. And to make this part easier, what we actually provide is we provide templates, first of all. So let's say we have an empty skeleton with just blocks saying, or if you want to integrate your robot here, fill this code snippet with how you tell your robot to go from point A to point B, and that's it. Or like, for example, we have templates, and we also have like examples, so which is more of a fully functioned example that runs in simulation that people can just simulate and then like change pieces of code. But most importantly, we provide a bunch of reference implementations for vendors that have an open API and we work with throughout the years. And we provide a list called awesome adapters of just community-driven open source implementations for all sorts of like robots or doors or lifts that people can just use in their own project and use as they wish. So as I mentioned just now, we need to deal with the fact that different robots will give us different access to the will give us different APIs. So we deal with this by having by grouping the APIs in the levels of control into three big blocks. So you have the full control on the left, which is when our robot vendors allows us, as it says, full control of the robot. So we can start it, we can stop it, we can tell it to go to arbitrary waypoints, and the robot will do it. Then if some robots don't give you access to this, but they just give you access to an API that only allows you to pause and resume. So we call it traffic light because it's really analogous to how a traffic light works. And then finally, there is in some cases, you need to deal with robots that actually will not give you any sort of control, and they will just report you where they are over time. And this is what we call the read-only integration. Now, what is you can see kind of the trade-off matrix over here, and generally the full control is the type of API that allows us optimal traffic flow and resolving complex conflicts, while traffic light allows some level of conflict management, while read-only, for each read-only robot that we have, the only thing we can do is reroute other robots and tell them to avoid it. So that's the least flexible type of control, the integration that we have. But we're also so this is the current state of things, but we're also working on future work as a native integration. So this will be especially useful for ROS-2 based robots. So we plan to have a native integration with the ROS-2 nav stack, so that RMF can fully integrate with the onboard perception and, for example, the robot cost map, and can resolve conflicts and do planning on the robot itself. But this is part of the future work that we'll be doing in the future. So this is a classic toy example of how RMF works. So the two robots with the video is not playing. The two robots have been asked to go to opposite side of the corridor, and the naive solution would involve. Let me see if this works. Yeah, it works. So the naive solution would involve only the two robots sharing the same corridor, but this is of course not possible. So RMF solves it by maybe for some robot taking a slightly longer route, but making sure that they can both it's a semi-optimal solution where both of them can reach their goals. And this is another case where sometime you don't have these are another of our demo scenarios that we use to stress test our systems. And sometimes you don't have the luxury of having extra corridors or places, other places that the robots can go to. And when this is the case, robots will be instructed to wait at a point until the corridor that they need to use is available. So for example, here we will see that this robot needs to go down, but it will wait until basically it will wait in place until the other robot that it needs to share the corridor with reach the destination, and the corridor is free. So now the corridor should become free, and the robot will start moving, and they will share intersections and so on. And another important aspect, as I mentioned, is the idea of sharing infrastructure. So in this case, there is only one corridor, and robots need to need to go through that corridor and use one door. And the idea is that robots will take turns to communicate with the door and command it to open it and close it, and then with RMF taking care of this coordination. And one of the important points here is that any system integrator, if they want to bring in, let's say, if they have a site with 3 fleet vendors and 5 door vendors, and they want to bring a new door in, they just need to write an integration once to get the door to integrate it with OpenRMF. And once that happens, all the robots will automatically be integrated with the door already. And the same happens for lifts. This is in contrast with what traditionally the approach is, where traditionally nowadays most robots need to communicate directly with like doors and lifts. So if you had to, let's say, bring a new door, you would need to like write 5 integrations if you have like 5 brands of robots. So another part that I mentioned that RMF takes care of is this idea of a task. So robots, of course, are only useful if they can do tasks. And the way we define tasks is by using this concept of a task description, which is a data structure that can be interpreted into a predictive model. And the predictive model includes like the initial state and like a model of the robot, and uses this data to output a prediction state, to output a predicted state. And this is used to, as I mentioned previously, you need to have this idea of what the lowest cost is and what's the optimal robot to execute a task. And this is how it's done by estimating like the state at the output and choosing the robot with the lowest cost. And then after this, the task is assigned, what we provide is a runtime, which breaks down a task into a sequence of phases. And phases are like primitives of like operations that a robot can do. Like for example, a task of like delivering an item can be broken into a phase of go to a point, open a door, move past the door, close the door, go to the door of the lift, call the lift, and like, and so on. And these are like, all phases needed to like take care of the task. And we also offer a way for human operators to either skip or repeat the phases, and this is very useful in some times when the phases don't go as intended. Like maybe if you told a robot to pick up an item or to clean an area, it didn't clean the area properly, so you want it to repeat the phase, and you can just ask it to repeat the phase. Now another like constraint of the current implementation and part that we are working on to add in the future is that currently a task is assigned to a single robot. There can only be and tasks cannot depend from each other. So what we will be working on in a future iteration of the task system is first of all collaborative tasks. So let's say a complex task that needs to be done by 2 robots collaborating. We will have support for that, and also constraints between tasks. So let's say you have task A that depends on like task B reaching a certain point. Then we will model this in a more comprehensive task system. So this is an example of task descriptions that the system integrators will probably like at some point handle within their life. So we provide like 2 different types of tasks. We provide like simple pre-made tasks that are designed to cover like very classic cases. Like in this case, you can see a delivery. So the robot has been instructed to deliver these few objects from the pharmacy to the bedside of the patient. And the idea is that the system integrator just needs to fill up, where to deliver to and like what items if they need to, and then RMF will take care of the rest. But we also like provide a custom API for users to define their own tasks. So over here, like if a user want some customization in this task, so they want, for example, to drop off the medication but also greet the patient. So again, like they can break it into cases. So they can say, okay, like pick up an item from the pharmacy, which is analogous to pick up an item from the pharmacy here. Then drop it off at the ward, which is the same. And then after this is done, they can define an additional action, which is in this case is like tell the robot to greet the patient in the Hokkien language, for example. And users can also specify custom cancellation behavior. So in this case, if the task is canceled before it's finished, the robot will be instructed to go back to the pharmacy to drop off the medication. And yeah, and you can see over there, and there is a link for like the documentation on how these tasks works and how to use them for your application. Then, as I mentioned before, there is this idea of like auctioning the tasks, so to find which robot is best suited to execute a task. And the way this works is that whenever the user asks for a certain task to be performed, let's say I want this area to be cleaned, there will be a bidding process. So like every fleet that has cleaning robots will say, oh, I can do it, and then it's going to take me 40 minutes. Then fleet B says, oh, it's going to take me 30 minutes, and then fleet C says, I cannot do it at all. So in this case, we minimize a cost, which is usually how long it takes to complete all the tasks, and then we assign the task to the robot to the fleet that will perform it with the lowest cost or shortest time in this case. And then finally, a last part of the system that we also provide is world building tools. So if some of you folks have been working with RMF for some time, you might be familiar with this tool that we had called the traffic editor, which is a 2D, pretty much like drawing annotation system. But we are working on a next version of the system, which will be 3D. And of course, we all know that 3D is strictly better than 2D. And the idea is that you can see in real, while you edit your buildings and you design and you you specify your robot behavior, you can like see in real time what the system will be like, and you can also like test scenarios in real time. So the idea is that it's a lot easier and it's a lot faster for people to iterate. Like for example, they can see, oh, if I tell the robot to go through this corridor, is it better or is it worse? Well, let me just draw a path here, click a button, and then I can test it, and then that should just work. So yeah, this is another thing that we are working on, which is the next iteration of our tools. And something that I've not mentioned in the beginning of the talk, but I guess it's the current state of things, which is that all that has been presented is actually fully open source. So we are part of the Open Robotics team at Intrinsic, and we maintain the OpenRMF GitHub organization. So all the stuff that you see over here is open source, and it's under a permissive license, the same as like ROS and Gazebo, which means that people can like download it, use it for the commercial applications, and they can like do pretty much whatever they want with it. That's it for me. Like, if you like it, go and check it out. If you contributions are welcome, or if you want to use it, don't contribute. Whatever, it's an open license. So enjoy it.
Thank you, Luca. All right. So now we'll kickstart the questions segment for Luca. If you guys have any questions, please feel free to ask away.
Hello, Pavel from X-Square, local HV producer. I have a question about conflict resolution. Are you assuming that vehicles are able to run around each other if they are different vendors, or maybe differently? How do you know that two vehicles can resolve this conflict in space? In time, of course, you can say, let's do this cleaning tomorrow, but in space, are two vehicles, how do you know, basically, that two vehicles can drive past each other?
So in RMF, like, you need to have like a model of your robot. As part of the model, you have a footprint of the robot. So given like, the size of your space and the size of the footprint, you can know, first of all, whether the robots can actually share the same corridor. But if they cannot, actually, what RMF will do is it will ask one of the robots to like move away from a corridor that needs to be used, and so to make way for the other robot.
So all arbitrary poses you need to assign manually all the time, right?
Wait, what? Sorry, you need to assign manually?
The give way poses. I don't. How do you call it?
So you basically in the current implementation, you design this. You configure the traffic flow by designing like a like a navigation graph. A navigation graph is just a topological graph with like points connected by edges. So let's say if a robot is going down along an edge, and another robot wants to come, but that would result in a conflict, one of the robots will be routed to a different edge, basically, if that makes sense.
Is there any other questions? Thank you first. Oh.
Hi. With now the current market with more IoT devices, do you have any plans for adapters for IoT, maybe cameras or LiDARs or sensors?
Yeah. Okay. So part of the I was mentioning before that part of the future work will be this integration with the ROS-2 navigation stack. So the idea is that like a robot itself will already have, let's say, either a LiDAR or a set of cameras, which will give some information about what's in the surrounding of the robot. So by doing that, I would say it's already kind of an implementation of an integration with like this kind of sensors. But we also have like different implementations out there. So part of some work that we did before was integrating with like cameras in a building, and like the cameras would, for example, like run detectors and tell RMF if there is like a lot of people in an area. And then RMF would accordingly, if it detects that there is a corridor that is very crowded, it will as like either penalize robots from going there or fully prevent robots from going there and reroute them to other areas. So yes, we have different types of integration, like different skeletons or different types of integration with like a variety of sensors.
Thank you. So it's more with the lane system, right? Is there any future implementation, like let's say detecting a human falling down or something?
Okay, so first of all, yeah, so it's currently we have a lane system, but like part of the work that we are also doing right now is to move more into free space planning, which is also what was necessary for this kind of like navigation stack integration. I think we have done some like simple like proof of concept works, as like maybe something like you have a camera, it detects maybe a person falling down, and then it automatically sends a task to request a robot to go to a place or something to check if something happened to the person. But in general, these are things that can be done at the higher level, because again, like, the API to send tasks is very simple. So you can just use one of these, like, of like AI implementations to maybe like send a camera and detect some event that happened and request a robot to do something as an action, I guess.
Okay, thank you.
All right. Maybe we can take one more question. I think the gentleman down there requested for Mercedes, right? Yeah.
For the fleet management, is all the robots connect to your IMF, the status being saved in the database? The robot status, the positions, all this information, where you save the information?
Yeah, so it's saved in a bunch of different places. So as you mentioned, so we have a part of the system is also that we have a web dashboard. So for the web dashboard, yeah, we have a classic like front end, back end system where every time a robot update comes, then we save it in a database. So if anyone like loads the web page, they can see what the latest status is. But some of it is actually ROS-2 based. So it's just like saving local memory, for example, for the nodes that need to do the traffic planning. But usually, yeah, we have at all points in time we have a persistent. We save the state in a persistent storage to also be able to like deal with like recovery behavior, I guess.
Just now, for your demo, for a corridor, right? The path is occupied by only one robot. But if the corridor is wide enough, can two robots use the same corridor?
Yes. So this is again up to the system integrator. So we like the way. So the graph is just assigned as lanes. So if you have like so it's similar to like lanes in a road. If you have a corridor that is very wide, you can design maybe like 2 or 3 parallel lanes, and you can even like decide unidirectional lanes, so robots can only go in one direction. So yeah, if you have enough space, you can definitely have multiple robots that go at the same time.
So for the existing one, for your existing open IMF, the path only occupied by one robot?
Yes, but you can just draw 2 paths parallel to each other, and that would allow you to have multiple robots.
Okay, thanks.
Thank you for the question. We've come to the end of the Q&A session for Luca. Thank you, everyone, and let's give a round of applause to Luca.